All right, hopefully the thing will pick up my horrible voice. All right, so up until now, everything we've been doing, we've been studying the motion of one object acted on by forces, right? Unfortunately, sometimes one force moves multiple objects, right? So for example, if I pull this desk, three things move, right? The desk, my water bottle, and this remote control, okay? So that example there would be what we call a system of objects, all right? My one force applied to the desk moved not just the desk, but also the water bottle and the controller, all right? And so what we're going to do today is talk about how you can figure out the acceleration of the individual objects and the forces that accelerate them. So like in this example, I didn't move the water bottle, I moved the desk, right? So what's the force that did move the water bottle? The desk, a little more specific. There you go, friction between the desk and the water bottle, right? Okay? So we should be able to figure out the force of how much force of friction there was to cause the water bottle to accelerate with the rest of the desk. Make sense? All right, so that's sort of where we're at. So we got three examples. So here we go. Well, that one was exciting. Why did I have that there? I don't know. Okay, so take a second, read the problem. Save my voice. I've got cough drops, but yeah, it doesn't really hurt. It's all scratchy.
Which one doesn't?
Sorry?
It's like it doesn't. If not, so.
I guess I gotta figure out this sinus infection or something.
Voice like that.
All right.
If I had a voice like that, my mom would still say this.
Okay, so.
Oh, I make it with my voice.
Thank you. All right, so here's the deal. When we do this, so what's happening is Roy is in here, right? He's. Well, the board needs to be calibrated. Okay, so anyway, so Roy is pushing box A. But box B is going to move, isn't it? They're both going to move, in fact, right? And so what we're going to do is we're going to figure out the acceleration of both boxes and then figure out how much force box A is exerting on B. Right? But remember, you guys, if box A is pushing box B, then box B is also pushing box A. So both of those forces are sort of at play here. All right? So usually when you solve a problem like this, you begin by looking at the system as a whole. All right? So what I'm going to do is for a minute, I'm going to pretend objects A and B are one big object. All right? And we're going to call that the system. So here's objects A and B. So what would my combined mass be? Just 80 kilograms, right? All right, and then there are three forces acting on the system. Specifically, gravity is pulling it down, the floor is holding it up. We can calculate those if we want, but they're not going to affect the problem, so I'm not worried about it. Cool? All right, ultimately what we're interested in is the fact that Roy is pushing all this stuff. So here's the force from Roy. He's pushing these boxes together with a force of 240 newtons. Are there any other forces? It's frictionless, so I think that's it, right? So we can find the acceleration then, right? So net force on the system would be 240 newtons, and therefore the acceleration would be net force over mass, 240 newtons acting on 80 kilograms. So you get 3 meters per second squared. Yes, sir.
All right, so he's pushing box A into box B. Wouldn't there be an action-reaction pair? Wouldn't box B push
I'm
back?
glad you said this. I was going to talk about this in a minute. Hold tight for 1 second. No, I guess I need to talk about it now. Okay, so what Max just said is he said since A is pushing B, B is pushing A, there's an action reaction, right? So why don't we need to take that into consideration? Right, so it turns out when you're drawing a free body diagram for an object or for a system, the only forces you have to worry about are what are called external forces. Okay? And by external forces, I mean the force has to be exerted by an object that is outside of the system. Right? If your car runs out of gas, you can't sit in the car and push on the dashboard and think the car is going to go. Okay? Because it's what we call an internal force. What's going to happen is you're going to push the dashboard, which then pushes you backwards. So now you're pushing the seat backwards, and the seat's pushing you forwards, and nothing's going to happen. Everything kind of cancels out, right? Okay? So when you make these drawings, all you need to worry about are the forces that come from outside of the system. Let me finish my train of thought. I got you. All right? So what Max is saying is, well, what about the force of A pushing B? That's for sure that's a force, but it's an internal force, not external. Okay? That's sitting inside the car and pushing the dashboard, all right? Sloppily, you could think of it in terms of, well, yes, A is pushing B, but B is pushing A, and those cancel. That's a little bit sloppy because they act on different objects. But since both of those objects are within the same system, it may not matter. Okay? So in a minute, Max, what we're going to do is we're going to make a free body diagram for just box A. And then we're going to make a free body diagram for just box B. Then we'll have to worry about those forces. Does that make a little bit of sense? Let me finish the problem, and then if you have questions about that again, then I'll talk about it more. Is that fair?
Yep.
Okay, yeah, Fred.
Does it not matter because when both boxes are at rest, are they still putting a force on each other?
Not unless Roy is pushing them. Right? Like right now, my desk is touching the sink over there, but they're not pushing each other. But if I try to move the desk, now the sink is pushing the desk. All right, everybody good? Yeah.
Won't the two objects have like different coefficients of friction as well as inertias?
Different inertias is different masses. So 100% yes. They have different masses, so they have different inertias.
So,
Different coefficients of friction depends on what they're made of. If these are both, wooden boxes sitting on a floor, then it's going to be the same coefficient of friction.
so do you have to like find the movement of box A and then change that to make it proportionate to box B?
Not exactly. You're way ahead of me. All right, we're doing frictionless right now. We'll get to friction in a little bit.
Okay.
Okay. It's on deck. All right. So is everybody okay within the scope of what we've done so far? All right. Great. So what we just found is we found the acceleration of the system. What this means is both of my boxes are going to accelerate this way with an acceleration of 3 meters per second squared. Cool. All right. So let's buy ourselves a little space here. Oh, that didn't do what I wanted it to. There we go. Okay, cool. So now let's look at the boxes individually. Box B is moving for some reason. Why is box B moving? Heard somebody whisper it. A is pushing it, right? Right. So for a minute, let's take a look at box B. And there's nothing magic behind me choosing B first. We could have chosen A first. Okay? I'm choosing B first because it turns out it's a little bit simpler because there's less forces on it. We'll see that in a minute. All right, so here's box B. So the mass of box B is 60 kilograms. So again, there's going to be a gravitational force pulling it down. There's going to be a normal force holding it up. Again, I don't care about those in this problem because they cancel out. And the thing that's pushing it forwards is the force of object A pushing it. Notice, Roy is not pushing box B. Roy is not pushing box B. He's pushing box A. Make sense? All right. So that's sort of as far as I can go with this. I could calculate my gravity and my normal force, but force A I can't find quite yet. To do that, I need to think a little bit more. There's one other thing that I know about box B. Yep, it is pushing back on box A, but that's going to affect box A. So I'm not going to worry about that until I make my drawing for box A. Does that make sense? Yes, you can. Yeah, right on. We know the acceleration. Acceleration is 3 meters a second squared, right? Good. So when you find the acceleration, you should immediately find the net force. So my net force is just going to be 60 times 3, right? All right, now, if my net force is 180, and the only force affecting the motion is box A, what does the force of box A have to be? 180 newtons, right? Right, because these guys cancel. There's no friction. Roy's not touching it. So that's it for box B. Right, and that works, right? Because then 180 divided by 60, which is the rate of acceleration. Follow? All right, now, the cool thing about these problems is once you get your answer, right? Because how much force will the two boxes exert on each other? 180 newtons, we just got it, right? We can check our answer by looking at the other box and making sure that all of our puzzle pieces fit together. All right? So let's do this. Let's buy ourselves a little room on the board. Excuse me. Let's look at box A. So here's box A, 20 kilograms. So I can put in my force of gravity and my normal force. I'm going to not worry about them because of time. Now, there are two other forces acting on A. One of them is given to us. What's that? Roy is pushing, right? Look, Roy's over here pushing box A with a force of 240 newtons. But there's another force. B, right? Check it out. A's not going to move as fast because B is in the way, right? B is pushing back on A. So over here we found the force of A pushing B. This is the force of B pushing A, right? So it should be negative 180. So there are two ways we can check our answer. Option one is assume that that's right and find the acceleration. What should we get? 3. Or assume the acceleration's right and find the force of B and hope that it's 180. Either way works. You got a preference? You want to just assume it's 180? Let's do it. So if this is positive 180, then this must be negative 180, right? All right, are there any other forces? That's it. All right, so what's our net force going to be here? Let's see, 240 minus 180, our net force is 60 newtons. And therefore my acceleration is going to be 60 over 20, which is 3 meters a second squared. Why am I happy? So we've got the same answer. Yeah.
Okay, so even though box A is being slowed down by the force of B because it has less mass, it still has the same acceleration.
Say that one more time. I
Okay,
think I lost track. Everything you just said was true. I guess were you just saying true or false? Were you asking
No.
right?
Yeah. So since it's losing some of its it's not being pushed with as much total force because of box B. It still has a similar acceleration because it has less mass.
Yes. Oh, I see. So like smaller net force. Yeah, you're right. So you have less net force. So here's a sloppy way of thinking about it. Roy has exerted 240 total newtons to get both boxes moving at the same rate, right? Okay. So the idea is box A uses 60 of the newtons, and box B uses 180 of the newtons. 60 plus 180 is 240. Notice box B uses 3 times as much force because it has 3 times as much mass, right?
Okay.
Kind of a sloppy way of thinking about it, but it works. Make sense, you guys? Questions with it? All right, cool. All right. I got that cough recorded. All right. Next example. Oh no. All right, so now we've got a pulley with 2 boxes. All right? So we haven't done anything with pulleys yet. Basically, all that a pulley does is it redirects a force. Okay? If there's a desk here and I'm going to lift it by using a pulley, I can lift it straight up, or if I run a rope up over a pulley, then I can lift it by pulling down. I haven't sort of gained any force, I've just redirected the force. Okay? Now, that being said, you can use systems of pulleys or ways of strategically using pulleys that does increase force and that kind of thing. But anyway, here's the deal. In this problem, we've got these two boxes, all right? Box A is 4 kilograms, B is 6 kilograms. They're just hanging there. So what's going to happen? Box B is going to go down, and box A is going to go up, right? Because B is heavier, right? All right. So what we want to do is we want to find the acceleration of, and I think I meant to put a box here. It doesn't matter. They're going to have the same acceleration, right? Because they're tied together. Okay. And then we got to find the tension in the string. All right. So the idea is this. Indirectly, B is pulling A up and A is pulling B down. Okay? But it's done by means of this string. The tension force sort of acts as a conduit for force. Okay? So, here we go. So we're going to solve this the same way we did the last one. We're going to start by looking at the system. All right, so here's box A. We can find the force of gravity on box A, right? It's just going to be 4 times 9.8 gives us 39.2 newtons. Don't make it negative. We'll talk about negatives in a minute. Don't make it negative. All right, gravity is pulling box A downward with a force of 39.2 newtons. Cool? All right, similarly, B is over here, also being pulled down with a force of 6 times 9.8, which is 58.8 newtons. Do I need to worry about, since I'm looking at the whole system here, do I need to worry about the force of the rope? No, because it's internal, right? We only worry about forces coming from outside the system. Gravity is a force that comes from the Earth, which is not in our system, right? Follow? Okay. Dan, you good?
Wait, why did you say it's not negative?
I haven't said that. I'm about to explain. All right, so here's why we didn't worry about the negatives. Both of these forces are pulling down, right? But are they working together in this problem?
Yes.
Are the two forces working with each other or against each other? Against each other, right? Because look, the pulley's here, right? So there are two possible ways the system can go. The system might go this way or it might go this way, right? It might go this way or it might go this way. Follow? So what we're going to do is we're going to pick one of those directions to be positive. It doesn't matter which one you do.
Oh, either one.
All right. So I always pick the one, the positive one to be the direction it's moving in. Just because it's sort of more intuitive to me. If you want to do it the other way, that's cool. But I'm going to make this way positive and this way negative. Which means this force of gravity over here is going to be positive, but this is working against it, so this one's going to be negative. And now for the rest of my problem, anytime there's a force working towards moving B down and A up, that's positive. Anything working towards moving A down and B up is negative. Does that make sense? Yes. The system can only go one of two ways, right? Either B is going to go down and A is going to go up, or vice versa, right? So I just said, let's pick one of those two directions to be positive. And I arbitrarily, totally arbitrarily chose having B going down as being positive. Good, up to there? All right, so what I'm saying is for the rest of the problem, if there's a force which is contributing to moving B down and A up, that's going to be positive. Right? Because it's going, somebody last hour expressed it as clockwise and counterclockwise. If you want to think that way, that's okay. Does that help?
I just like, I guess I just don't understand how force is positive and force down.
I think down being negative is arbitrary too. Like we just, as a educational society, have decided, let's make down on the y-axis negative. And we just all agree on it. But there's nothing magic about it. You can make down positive if you want. You just gotta stick with it. Okay? Let me think about a better way to explain that. Yeah.
Is, I think like positive is the sign is positive because like you were saying, it's working against you, so it's like I don't know. I guess it's
No, I know what you mean. But I mean, so basically what she's saying is that if A wasn't here, B would just be falling, right?
so
And A is working against that. Cool?
Yeah.
Okay, so I don't need to worry about tension, so that's kind of it, right? Those are the only forces I need to worry about, right? All right, so let's find our acceleration. So let's see. So for the whole system, our net force is going to be the force of gravity on A plus the force of gravity on B. So that's negative 39.2 plus 58.8 newtons. So you get 19.6 newtons for a net force. What should I do? Find the acceleration, right? By dividing by mass. What mass do I use?
Oh, wait, go ahead.
Both, because everything is accelerating this way, right? The whole system is going this way, right? Due to this net force acting on a total mass of 10 kilograms. Like, make sense, you guys? Questions? Cool. So, that's question A. All right, B's. Yeah, I did. Yeah. All right, so B says find the tension in the string. So really, you guys, this problem is almost identical to the one we just did, except it's gravity that's causing the system to accelerate instead of Roy pushing it. All right, so to do question B, we need to pick an object the tension is acting on. B works. You could just as easily pick A, right? So after I answer Christina's question, we're going to make a free body diagram for one of our two boxes. It doesn't matter which one. Yes. There's no tension. Well, no, there is tension. What I said was, in this drawing, we didn't need to worry about it because it was an internal force. Because the tension comes from the string. And here, my system is the two boxes of the string. Does that make sense?
Yeah.
So you only need to worry about forces that come from outside of your system. Here, the string was included in the system, so you didn't need to worry about the tension. Follow? Everybody good? Awesome. All right, so which box do we want to do? B, done. So here's box B. Here are the things I know about box B. I know that gravity is pulling it down with 58.8 newtons. Notice I'm still keeping it positive. So for this time, for this weirdness, we're going to have down as positive and up as negative. Okay? All right, what's our acceleration? 1.96, positive or negative? Positive, right? Because it's moving down, right? And then what's the only other force I don't have? Tension force. There's no normal force because it's not sitting on something.
That's the tension force.
Oh, shoot, I just said there's no normal force and then I wrote that. Sorry, somebody got in my head. All right, there's one other thing that I should do before I solve this thing. Find the net force, right? So net force is going to be mass times acceleration. So what mass do I use now? 6 kilograms, because I'm just focused on B. So that gives you 11 point, I think it's 7.6. Hello? Carmela, you doing okay there?
Wait, is that 1.7?
It's 11.76.
Okay. I thought that was.
That's the net force. That's the total of all of my forces. So now we got to do some algebra, and you guys are already headed there. Yeah. So let's see. So we got this. Yeah. Why? Because it's working against the downward motion. Remember, we decided down was positive, so up is negative. Right? So our net force is 11.76 newtons. That's got to equal my tension force plus 58.8 newtons from gravity. Subtract, and your tension force ends up being negative 47.04 newtons. Follow? Questions? When do we get out? 13?
That was 09.
Oh, 09. Didn't think I knew that by now. All right. Are we good?
We're all good.
All right, so technically what we should do at this point, what we should do at this point is go back and check box B and find the tension again. It's the exact same calculation. You find your net force, right? You know the force of gravity on A, and you find your tension again. And you should this time get positive 47, right? Because it's Newton's third law. This is indirectly, this is the force of A pulling B up. All right? You know what, let me just do it. I waffled on this last hour too. Let me just do it. Several, what do you got?
So for the answer, it says positive, but does it matter?
It's going to be positive at one end, negative at the other. So
we got the right answer.
yeah.
Okay.
Yeah.
The acceleration for box A be negative.
I don't know, which way is box A going? Positive direction, right? Remember, positive.
Why would the
So why
acceleration for box
I actually give it what's that?
Why would box B positive?
Somebody help me explain this more clearly than I have. Do you understand why, or are you asking a question?
So box B has a positive acceleration too, right?
Everything has a positive acceleration because everything is going this way.
Oh,
Everything is going this way.
that's
They're all one string.
It's all one string. The whole string is going this way. If the string had gone that way, then everything would have been negative.
All right, what I was thinking is A goes up, positive acceleration, B goes down, negative acceleration. But that's not right.
No.
So it's they both go this way, so it must be positive.
Did that make sense? And again, that's arbitrary. We could have, if we'd wanted to, we could have made this way all negative. But we, at the beginning, we decided, let's make this way positive.
So if it makes more sense to you to make it, flip it.
Then do that. Yeah,
How would you put this negative or positive?
it doesn't matter. That's what I'm saying. Just pick whatever is most intuitive. No, don't be sorry. Do you see what I'm saying? That there are two possible directions the system can go. It can either go this way, or it can go this way, right? So pick one of those directions to be positive and then stick with it. Good? Everybody good? All right. Do I need to do box B? You guys understand it's the same thing? Everybody good? All right. Okay. Read it.
Oh, shit.
Oh no, why did we do this?
As soon as I read 40, I was done. You are sick.
What?
I bet you sound like Kentucky.
You're sick. Oh,
In the
Okay.
way. Turn me sick.
All right, so Donald is up here grumbling about the fact that this just got harder. Sure, this just got harder. All right. So here's the deal. So let's think about this system. I can think of at least two and probably three forces that are going to affect the motion of the system. All right, but again, this is one of those things where, look, my system can either go this way if the 30 kilograms is winning, or it can go this way if the 25 kilograms is winning. In this one, it's pretty obvious which one's going to win, right? Because this is both heavier and not on an inclined plane, okay? So I am going to totally arbitrarily make this way positive and this way negative. Why? Because I like doing it that way. If you want to do it the other way, then do it the other way. It does not matter at all.
You want this to live in pictures? Is that all?
No, I'll be able to figure it out as long as they're consistent. All right, there was a handoff before.
Which one of them is frictionless and which one's not?
Oh, I'm sorry. I forgot about that. There's a typo. Sorry. I originally had it written as frictionless. The reason I gave you guys new notes, I realized that the examples here were way easier than homework problems. So I ramped up the difficulty on the notes and downgraded a little bit of difficulty on homework. What's wrong? You failed. Okay. All right. Sorry. All right. So, name the forces. What there are, I can think of at least 3 forces now that are going to affect the motion of the second Taylor.
The force of gravity perpendicular, the force of gravity parallel.
Slow down for me for a minute. No, you're good. You're good. So, the force of gravity perpendicularized this way. Is that contributing to it going this way or that way? Yeah, neither. Right. Because it's going to be canceled out by the normal force anyway.
Man.
You see what I'm saying? There's 2 forces here. There's going to be a normal force and a perpendicular force. Those cancel each other out. But the parallel force is totally going to matter, right? Taylor, do you see why?
Yeah.
Everybody?
Yeah.
All right. So my force of gravity parallel is going to be in a negative direction. What else? They'll do friction. I think we all know what's going to happen, but hold off on it for 1 second. Before we do friction, there's one other force. Gravity on the other box. Let's name these guys. Let's call this one A and let's call this one B. So this is A and B. All right, now we can do friction. Now we can do friction. Which one of these 2 forces is going to win? Isn't B going to win? Right, B is going to win. So the system is going to move this way, so which way, point for me, which way is friction going to go? What kind of friction? We don't know yet. We don't know what kind of friction. All right? So here's my recommendation. Once you know you've got an object on an inclined plane, go over to the side and figure out all your sort of stats for that object. So here are the things that I know about object A. I know that the force of gravity on it is 245 newtons. I'm not going to worry about any negatives here. I'm just going to write down the numbers, all positive. Right? So that's just 25 times 9.8. Yesterday we learned how to calculate the parallel and perpendicular components. So I'm just going to, this is ft sine theta and ft cosine theta. And we know our theta is 40 degrees. So this one gives you 157.5, let's call it. And this one's 187.7. That means there's going to be a normal force, also 187.7. Everybody good? What are you saying? Sure? All right. All right. So there's a whole bunch of stuff that you can calculate for object A. These guys are just sine and cosine. These guys are just coefficient times normal force, right? Find the frictions. Everybody cool? What's that?
Number of subscripts
Yeah.
on force step. I know, right?
Sorry? No, because there's only 2 forces on object B, just gravity and tension. So the only reason I did this was just because there's a lot going on with object A. All right, so let's put in some numbers. So this guy over here, this force of gravity is going to be 294, just 30 times 9.8. What goes over here? Good, negative 157.5. All right, so they're placed there at rest. Does it move? What do we need to look at? Friction. What kind of friction?
Static.
Static. So static friction is 75 newtons in equality. Is that enough to prevent the motion? No, because 157 plus 75 is not going to get us to 294, right? So, there's not enough. So my kinetic friction is negative 46.9 newtons. Hello? Everybody okay with how I need to jump to kinetic? Yeah.
So it's negative 157.5. So would it have to be like a lot bigger to get? What I'm confused on is like, would it have to be more negative, the force of gravity parallel?
To get it to go this way instead of that way? Yes, that's correct. So yeah, if this was like a 50 kilogram box,
Yeah.
then this would be like 300 and something, and then the system would go this way.
Okay.
Follow? And then I would have switched my positive and negative sign convention. But we good? All right. So what should I do now? Are there any other forces that are going to affect the motion? Nope, because perpendicular and normal are going to cancel. So find your net force. It's going to be 294 plus negative 46.9 plus negative 157.5. And you get a net force of 89.6 newtons. So what should I do now? Find the acceleration, right? Divided by mass. Wow, I feel like that weights. What's my mass? So that gives you an acceleration of 1.62. All right, so what we just figured out, you guys, is my whole system is accelerating this way at 1.62 meters a second squared. So box B is going down at 1.62 meters a second squared. Box A is going up the ramp at 1.62 meters a second squared. Cool? Yes, sir.
So if you had paper offset,
Exactly. Yeah, so if you used a different sign convention, then all of your positives and negatives here would be switched. Literally all of them. Cool? Right, so we're almost done. Now we just got to find the tension of the rope. Did we get this right? Rounding, but yeah, we got it. Okay. Oh no. All right, finding the tension in the rope is easy. Which object do I want to look at to find the tension? B, right? I'm doing the best I can, you guys. It's okay. I can't wait to listen to the video later. Okay, something like that. All right, so gravity's pulling this guy down with a force of 294 newtons. I'm still sticking with making it positive. All right, what's the other force? Tension. So we know our acceleration. Find the net force, find your tension. Okay? All right, so look, I know my acceleration is 1.62 meters per second squared. So my net force is just going to be 30 times that, right? So that's going to give me 48 point something, 6 newtons, something like that. So then the question is, what does the tension have to be to make that happen? Well, let's see, net force is force of gravity plus force of tension. So 48.6 equals 294 plus Ft and solve, and you end up getting 245 newtons. Negative, because it's working against that downward motion. Cool? All right. Yes.
Did you just choose B?
Yeah, we could have just done object A. I chose B just because it needed to worry about friction. Hold on.
Oh.
Right, it just was easier. It was less to worry about. All right, now, quick comment. Somebody pointed this out last hour. It is totally 100% coincidence that this number and this number are the same. That is just a random chance. That doesn't mean anything. Literally means nothing. Okay? It's just because of the number of things. All right, questions? All right. So